Swayam Prabha. Digital India. Educated India.
So, warm welcome to the 19th lecture on the subject of digital signal processing and its applications. Let us take a few minutes to recapitulate what we did in the previous lecture. In the previous lecture, we had begun discussing the synthesis of discrete time systems, in fact the synthesis of digital filters. We had looked at the ideal filters, the four ideal filters that we most commonly encounter, namely the ideal low pass filter, the ideal high pass filter, band pass filter and band stop filter. I had taken the specific instance of the ideal low pass filter and we had looked at the impulse response of the ideal low pass filter. From the impulse response, we had drawn in fact, from the frequency response, the ideal frequency response, and from the impulse response, we had drawn three conclusions. The first one was that the filter was, of course, non-causal, but unfortunately, it could not even be made causal if we allowed a delay, a finite delay. So, by introducing a finite delay, we could not make the filter causal because the number of non-zero samples on the negative side of n was infinite. So, you see, if it were finite, if you have a finite number of negative samples or samples on negative n, then you can take the farthest back sample. So, for example, suppose you have samples which are non-zero for negative n all the way from n going from 0 to n going to minus 20. You can introduce a delay of 20 samples and make the filter causal. So, if you have a finite number of non-zero samples on the negative side, it is always possible to make the filter causal even if it is non-causal to begin with. But unfortunately, that is not the case with the ideal filter. Secondly, we noted that the ideal filter was unstable. We took the specific example of omega c equal to pi by 2. But I encourage you to take other examples of omega c as well. So, you could look at omega c equal to pi by 4 if you like, or 3 pi by 4 or some other values. And convince yourself that in each of these cases, the filter would become unstable. In fact, I put it before you as a challenge to show that for general omega c, this filter is unstable. That is a bit of a more demanding challenge. We had shown it for the specific case of omega c equal to pi by 2, but show it more generally for any omega c between 0 and pi, that the filter is unstable, right. Essentially, you will need to show that the filter impulse response is non-summable, non-absolutely summable, okay. Thirdly, we noted that the ideal filter was irrational, and that was because we could not have a continuum of zeros in the frequency response if the filter were rational. Now, of course, some people like to talk about what is called the Paley-Wiener criterion. You know, personally, at this stage, I think it's adequate to note that for a rational function, you cannot have a continuum of zeros as we do in the ideal filter. And in fact, because the ideal filter is irrational, we are now left with the trouble that it's unrealizable. So, on all these counts, the filter is describable but not realizable. Describable means you could put down an impulse response for it. You could describe what it does, but you can never realize it.